I'm here to walk you through the steps of a 3-point Testcross linkage problem. So using the example that I used in lecture, we're going to start out with the very first step, which is to identify which genotypes or phenotypes. In this case, genotypes are given, but in other cases you may just get the phenotypes, and you'll have to infer the genotypes from the phenotypes. So we identify the parental or the non-recombinant progeny. These are the ones that are most abundant here. And I want to actually point out that the nature of the Testcross is when we take in this case, a triple heterozygous individual with a recessive homozygous individual. And this individual can, in the presence of recombination, create every possible gamete combination. And this is essentially what we're seeing here. Whoops. And this individual can only create a single gamete, which is ST, little st, or mutant ST, mutant E, and mutant SS. And so what we're seeing here is down here in the second chromosome that we see, they all come from this individual. So they can essentially be disregarded. And the phenotype that we're seeing reflects the gamete that came from the heterozygous individual. So that's why we set up the Testcross the way that we do. And what we're actually measuring is recombination in the heterozygote parent. Alright, so step 2, we identify the non-recombinant progeny based on the number of progeny of that particular genotype or phenotype. Then we identify the double crossover progeny, and these are the least abundant ones. And based on by comparing the parental configurations and the double crossover configurations, we're going to identify which of the loci is in the middle. And what we do is we compare the parental configurations and determine in both of the double crossovers which locus is different than what we see in the parentals. So in this case, it's a fairly straightforward example because the parental genotypes are either all dominant or all recessive. And so in the double crossover, we are always going to have 2 dominant and 1 recessive, or 2 recessive and 1 dominant. And it's the one that's the locus that is the 1. In this case, the 1 dominant, and in this case, the 1 recessive. They're both going to always be the same locus because that's the nature of the crossover. And so we determine that SS here is in the middle. Once we determine that, we're going to want to rewrite on a test problem or on an exercise. You're going to want to rewrite the alleles to reflect which one is actually in the middle. And so here they've done that for you. Now SS is in the middle, same order that we had before. And what we're going to do now is our step 4 is to identify the where the crossover events happen. And so in our double heterozygotes, we know because they're double heterozygotes, double crossovers, that the crossover events happen in both places by definition. Okay, and so we can just automatically draw slashes right there for our double heterozygotes. Then we can go to each of our, here are our parentals, and here are ones for which we have just a single crossover event. In order to determine where that happens, we need to compare the genotypes that we're seeing with the genotypes in the parentals. And in this case, we're going to have 2, basically in all cases, we're going to have 1 allele that doesn't quite match the others. Here are the parentals, they're all dominant or all recessive. Here we have 2 recessive and 1 dominant. Therefore we know that the crossover event happened between ST and SS. So we're going to put the slash there, And same on the other one, because these are this is the other result of the crossover event. And then down here we have a dominant, dominant, and recessive, so that we know that the crossover event happened here. So we're going to put a slash there and there. All right, so now we've identified our recombination events, and so we've done step 4, which is determine where the crossover events occurred. And then in step 5, we're going to calculate the recombination frequencies for one gene pair at a time. So starting out with STSS, the recombination frequency is just going to be the number of individuals who have that who had that crossover event, divided by the total. So 50, you add up 50 plus 52 plus 5 plus 3. And divide that by the total, which is 755. Multiply that by 100, and we get 14.6% recombination frequency. For the second locus, or second pair of loci, the SS to E distance we calculate, we can do the same thing. 43 plus 41 plus 5 plus 3. Note that the double crossovers are included in both calculations. And then from there we can draw a map of between ST and SS we have 14.6 map units, and between SS and E we have 12.2 map units.